Hello guys. Let me move me over here so I don't block anything. This is the Aviation Gleim weather review. So I thought the internet was kind of lacking any review on all the chapters, so that's what I'm gonna be working on. And just so you know, I'm not a professor or anything. I'm just a college student. So if I get something wrong, just leave a hate comment for me, and I guess I'll know for when I take the private pilot test. Okay? All right. Let's go. All right. 7.1. All weather is related to a heat exchange. So if there's some sort of heat exchange going on, there's some sort of weather going on. Unequal heating will cause variation in an altimeter setting because unequal heating will change pressure, and pressure is what affects altimeters. So they are directly related, but that is why. The Coriolis force. So in the northern hemisphere, the wind will deflect right, and in the south hemisphere, wind will deflect left. This is caused by the Earth's rotation. Deflections are weaker closer to the surface because of the friction between the wind and the Earth. All right, so farther down you are, the less you have to worry about these. And here's a good photo of what's going on for the Coriolis effect. So we have the wind here going north, and you can see that it's going off right, and that's the right of that, and then left, left. So, yes. All right, now we have a question. What causes variation in an altimeter settings between weather reporting points? And just pause it here and answer. And the answer is unequal heating of Earth's surface. At first, low key, I answer variation in terrain elevation because I just know like altimeter and like if you're higher up. I don't know. It was fucking wrong. It's A. Don't get it confused. I think it's because this is like related to the ground and this is actually related to pressure and stuff because of heating. So, yeah. All right, this is me trying to explain convection currents. I had to draw it out.
Hello, I'm an air molecule and I'm hanging out over the ocean, and all my friends are hanging out over the ocean too. But low key, I look over here and I see there's literally like barely anybody over here. So I decide I'm gonna try and fill in over here. So I go over here because I just hate gaps and I want to fill in this gap. And what I've just done here is created a sea breeze. Because all I'm trying to do is try and fill in these warm gaps and get away from this dense gap. But now that I'm here, I'm over the warm land. And that makes me rise up. Rise up.
Rise up.
And now I'm up here. And when I look to my right, to my dismay, there is another gap. Because all my friends who had gone through this process had gone over here and apparently went down. But I don't know that yet. So I decide I'm going to go this way, try and fill in here, but actually nobody's up here because it's really cold out over here over the ocean. So I go down back to this crowded area, and then the whole entire cycle repeats. And what I did up here, forgot to say, is the return flow.
So yeah, that's a convection current. It doesn't just happen over the ocean, to my knowledge. Um, So, depending on the time of day, so if it's night or daytime, everything just kind of reverses. It's the same thing, it just reverses because water cools slower than land. So at night the water will be warmer than the land, therefore everything reverses, okay? All right, thermals. Those are rising columns of air caused by the sun. Uneven heating will cause pockets of warm air to rise and cold air to lower, creating updrafts and downdrafts. So watch out for those. So pavement and rocky patches in a field will cause an updraft because like dark objects like that and like rocks and shit, those will absorb heat. And then oceans and lakes will cause a downdraft because they don't absorb as much heat. This can cause turbulence on your intended flight path and knock you off your landing. So be careful, okay? Um, let's do a 7.2 question. Convection current circulation patterns associated with sea breezes are caused by warm, dense air moving inland from over the water, water absorbing and radiating heat faster than the land, and cool, dense air moving inland from over the water? And the answer is C. Cool, dense air moving inland from over the water. You really just have to think about it and like make sure you don't mess anything up because like number A is literally just reversed if it was at nighttime, you know. So, but that would be a land breeze. So, um, or it would be actually not. I don't know. Never mind. Don't listen to that. um, okay. 7.3. So a front, we're getting into weather, like real clouds shit up there. Um, is an area of high pressure and low pressure system. So a high pressure system is descending air or a high pressure system is descending air, low pressure system is rising air. Um, just see, because you can think of it as like the atmosphere, like the air is rising and it's like expanding, therefore there's like less pressure. And then when the air is descending, it's getting like smaller, so there's more pressure. So that's why it's high and low pressure. Um, when you cross a front, air temperature and wind direction should change. So that's a good indicator of if you are crossing a front. So, types of fronts. So, we got the warm front, and that's where temperature rises. There's clouds and light precipitation, and it's just warm air replacing cold air. And then there's the cold front, the more dangerous of these two, and it's the temperature will decrease. There will be clouds, heavy rain, and thunderstorms. But after passage, expect clear skies but very gusty winds. And that's just the opposite of warm front. The cold air is replacing warm air. And then we have a stationary front, which is calm winds, possible prolonged clouds or rains, and it's where neither air masses are strong enough to remove the other, resulting in a stall. So basically, the air masses are just meeting like this and they're equal strength. It's like Hiroshima and Tetsu Tetsu Tetsu, okay? They neither can take each other down. And then we got the oscillated front. Um, it shows characteristics from either warm or cold front, and they tend to be more severe. Um, Combination of cold and warm air. The cold air will be at the bottom, and the warm air will be at the top. So there's a temperature inversion going on here. So when you are looking at a map for these, the blue lines will indicate a cold front. Red lines will indicate a warm front. A stationary front will be red and blue, which are like right here. And then an oscillated front will be purple. So that's how you know. All right. One of the most easily recognized discontinues across a front is a change in temperature, an increase in cloud coverage, and an increase in relative humidity. And it's a change in temperature. The temperature will change depending on, you know, if you're going from a warm to a cold front or whatever, high pressure, temperature changes, to my knowledge. Okay, now we're on to thunderstorms. For a thunderstorm to form, we need sufficient water vapor, an unstable lapse rate, and I was like, what is that? What is a lapse rate? It's when air temperature decreases with a height faster than the dry adiabatic lapse rate. So, the dry adiabatic lapse rate, or the DALR, is the rate at which a parcel of dry air cools as it rises. So that's 5.5 degrees Fahrenheit per 1,000 feet. When air temperature decreases faster than DLAR, air parcels remain warmer than the surrounding, allowing them to rise, creating vertical developments and convections. And then, also an air parcel is just a measurement of air. That's just what they use. Um, and then we have the initial boost upward slash updraft, and those can be caused by multiple things. So things that can cause a boost. We got the convection lift, which is like the sun creating like summer storms, just like, you know. Then we have the frontal lift, which is caused by the two fronts meeting. We just went over. Then we got the orographal lift, which is air forced to rise over terrain. If this like happens near mountains, and that can create it. And then we have convergence when winds are hitting each other, forcing them to go up, creating powerful storms like hurricanes and cyclones. That's why they're like happening near the equator because that's where the winds like to switch directions, you know, all the way back to like the Coriolis effect, I'm pretty sure. All right, so there's three phases of thunderstorm. We got the cumulus, which is the building of the storm, and it's all updrafts. And then we have mature, which is commenced by the starting of rain. They all apparently they always ask that question: what commences a thunderstorm? It's the rain. So there will be updrafts and there will be downdrafts. And the downdrafts are caused by the rain dragging all the air down with it. And then dissipating would only be downdrafts, and it kind of rains itself out, so it kind of just like squishes itself down like that. Um, using the rain. So then we got wind shear turbulence. So you can get some from a storm, which will kind of look like this, where it's like, you know, you would get a headwind and kind of go up, and then a tailwind and kind of go down. Or from a temperature inversion, which we'll get into more later, which is like these circles. See, it's getting pushed down and then it's getting pushed up. So look out for that wind shear turbulence. Um, Adverse winds are always found in thunderstorms and around them. Always expect that. Winds can be found a few miles away from small thunderstorms and hundreds of miles away from storms like hurricanes. Do not fly under the anvil of a storm. Potential for extreme air turbulence, and there's hail. So this is what the anvil of the storm looks like. It's it's the very top of it where it like, the anvil part. I don't know. That's what it is. So now we have squall line thunderstorms. Watch out for these bad boys. It has severe conditions such as heavy hail, destructive winds, and tornadoes. Hail should be anticipated with any storm while flying under the anvil, but usually ahead of a cold front is where the squall lines form. Squall line thunderstorms are more powerful than normal thunderstorms because they form dynamic heating such as cold fronts, whereas normal thunderstorms form from daily solar heating. Squall storms tend to last much longer as well, so watch out for these. All thunderstorms have lightning. If there's thunder, there's lightning. Small aircrafts are not equipped to taking lightning strikes like how commercial planes are, so completely avoid it. You won't be able to get it. Yeah, if you are hit, expect some permanent damage to your avionics or glass flight displays and possibility for structural damage. And the only prevention is avoidance. Don't go into the storm, man. Just stay away from that. Embedded thunderstorms. Storms you cannot see because they occur in cloudy conditions. These occur in bigger weather systems such as squall lines or mountainous regions. So, those can happen. Look out. All right, 7.4 question. The destination of an airport only has one runway, 826, and the wind is calm. The normal approach is calm wind in the left-hand pattern to runway 8. There is no other traffic at the airport. A thunderstorm about 6 miles west is beginning its mature stage, and the rain is starting to fall to reach the ground. The pilot should decide to depart expecting the thunderstorm to dissipate prior to arrival, then land on runway 8, delay departure until the thunderstorm has dissipated, or fly an approach to runway 26 since any unexpected wind due to the storm will be westerly. And the answer is B. Don't mess with the fucking storms, man. Just wait. Delay departure until the thunderstorm has dissipated, okay? Alright. Now we're on to icing. So structural icing requires two things. A flight through visible moisture. Invisible moisture would be like clouds, rain, fog, snow, hail, etc. So things you can see. And temperature will have to be at or below freezing, which is 32 degrees Fahrenheit or 0 degrees Celsius. Freezing rain usually causes the greatest accumulation of structural ice. Ice pellets are caused by when rain droplets freeze at a higher altitude. This is caused by a temperature inversion. So as you can see, we have ice pellets, and the warm air is on top actually instead of the cold air, and that's why we got ice pellets. And then there's snow, which is just by like normal, and then we got freezing rain, and then we have rain. So yeah, and I would watch out for icing in these two the most, apparently. Frost forms when a structure is at or below dew point, and I low-key just copied what dew point meant. It's the atmospheric temperature varying according to pressure and humidity, which water droplets begin to condense and dew can form. And temperature is below freezing. So water vapor will skip its liquid phase and immediately form into frost on the wing surface. So that's what's happening. Watch out for that. Um, Effects of frost, it will disrupt smooth airflow, causing airflow separation from the wing, which we can see in this photo here of like what would happen. There's a decrease in lift, there's causes of friction increase, and then there's increased drag. Frost should be removed before takeoff. Frost can make it difficult or impossible to take off. So don't mess with it. Take it off no matter what. Don't let don't let there be frost, I guess. Okay. One in-flight condition necessary for structural icing to form is small temperature slash dew point spread, stratiform clouds, or visible moisture. And the answer is C, visible moisture. There's always going to be visible moisture. You're always going to be going through clouds or hail or rain or something, okay? All right. 7.6, we got lenticular clouds. So these are almond-shaped clouds that form on the leeward side of the mountain. And if you're like, what is leeward? It's just the opposite of windward. So wind's always going to be hitting one side of the mountain. The other side is called the leeward side. So that's what it kind of shows up here. It can have up to 50 knots of winds. And it appears stationary as the wind blows through them. So it can be like kind of an illusion. Expect mountain wave turbulence when air is stable. Winds 40 knots or greater blow a course to a mountain. Um, Under each wave crest is a rotor turbulence, and it's more severe. And it's the most severe, the rotor cloud. So that's right here. That's the most severe turbulence. I don't know what I meant by a course of mountain. Um, I don't know. It's been a long week trying to study and make these slides, but ignore that. So hopefully that was somewhat informational. Anyways, an almond or lens-shaped cloud which appears stationary but may contain winds up to 50 knots or more is referred to as inactive frontal cloud, funnel cloud, or lenticular cloud. And it's the lenticular cloud. It's the only thing we went over in that unit. So that's the mountain wave stuff. All right, 7.7. Wind shear can occur horizontally or vertically, anywhere, as long as air is flowing in different directions or speeds. During temperature inversions, 2,000 feet to 4,000 feet, AGL, expect wind shear up to 25 knots, and those are like low ground level temperature inversions. Hazardous wind shears occur when low level temperature inversions, which is inversions occurring near the surface of the Earth, frontal zones where two fronts meet, and clear air turbulence or CAT, which can be caused by things like jet streams. So look out for that. Um, when may hazardous wind shear be expected in? When stable air crosses a mountain barrier where it tends to flow into a layer, forming lenticular clouds, an area of low level temperature inversion, frontal zones, and clear air turbulence, following a frontal passage where stratocumulus clouds form, indicating mechanical mixing. And the answer is B. It's the only thing we went over again for this, so it's not very much of a trick question. We're gonna find that many hard questions, but yeah. You just need the low level temperature inversion, frontal zone, and clear air turbulence. Alright. Air temperature within 5 degrees Fahrenheit of the dew point and decreasing spread, and a spread is the distance between between the two temperatures, so the air temperature and the dew point temperature, I think. Um, Expect fog or low clouds. So when the temperature of the dew point equals air has 100% humidity. So when the temperature is at the dew point, air has 100% humidity, and this is also called saturated air, okay? Um, Air temperature determines the amount of water that can be held. Higher air temperature has higher energy, allowing more water molecules to remain vapor before condensing into liquid at the dew point. So basically, more water molecules will fit into higher air temperature and it will chill there for longer, therefore more stuff in there. And the relationship kind of looks like this. That's the chart. My face was covering it. Um Water vapor will become visible when it condenses into clouds, fogs, or dew. So, yeah. Um okay. So, there's three definitions of stuff. Evaporation, liquid to gas, so like liquid to water vapor. Sublimation, which is a solid directly to a gas, which is ice to like water vapor. This is like aviation terms, sort of. And then deposition, which is gaseous directly to a solid, which would be like water vapor to frost on a like an airplane. And then there's a bunch of types of fog. So we have radiation fog, which occurs at night. I don't know why they don't say that in the Gleim, but it occurs at night. During no cloud cover, and the ground is still warm for the day, and it releases heat into the cold night air, forming the fog. Um, then we have advocation fog, which is moist air turns into fog as it's blown over a cooler surface. And then there's upslope fog, which occurs near sloped terrain like mountains, like a mountain range, where moist, cooled air is pushed up by the higher altitude, and it's like forced into a it's like it's okay. It's forced up and it cools because of the terrain. That's what I'm trying to say. And then precipitation-induced fog is when warm rain falls through a cold layer of dry air, usually associated with fronts. Dusk, there's a risk of icing, turbulence, and thunderstorm. And then there's steam fog, where cold land air passes over warm waters. Mild turbulence can occur and high risk of icing. So, precipitation induced fog and steam fog is like fog I would be looking out for. Not gonna lie. Seems like the scariest. Um, so what is meant by the term dew point? The temperature at which condensation and evaporation are equal, the temperature at which the dew will always form, and the temperature at which air must be cooled to become saturated. And it's the temperature at which the air must be cooled to become saturated. So if you hear air saturated, think dew point, okay? All right, we got four cloud families. We're back to clouds, guys. We got the high clouds, the middle clouds, low clouds, and vertical development clouds. And if you're researching the cloud families, you might see like cirrus, astrostratus, and those are just clouds, like the most common clouds that um like live in those families, but they are not the actual family name, okay? Um, so cumulonimbus clouds, nimbus equals rain clouds. We're gonna cover a lot of things from the thunderstorm again, thunderstorm chapter or section. So a towering cumulus is the early stage of a cumulonimbus, and that indicates a convective turbulence. The lifting action, unstable air, and moisture air are the ingredients to form a cumulonimbus cloud, and those are the same ingredients for thunderstorm, obviously, because they're the same thing. Um, all right, now we're gonna do some math, and it's actually not that hard. Okay, so estimating the base of a cumulus cloud formula. So where will the base of the cloud be? So you're gonna take the surface dew point and the surface temperature and subtract that, and that's where you get the dew point spread. So we have 69 degrees for the dew point, surface temperature 56 degrees, which equals 13 degrees Fahrenheit. And then the temperature of the dew point, which is 13 degrees, will be divided by 4.4 degrees Fahrenheit, which will get approximately 3. It's actually like 2.9. So that's the approximate above ground level in thousands. And since you want to get the real number, you just times that by 1,000, then you get 3,000 feet above ground level of where the cumulus cloud will form. Okay? And just to explain that, so a dew point, the temperature dew point converge at 4.4 Fahrenheit and 1,000 feet, um, divided by 1,000 feet. So that's why it's in the equation. Clouds will form when the dew point is 0 degrees Fahrenheit. So temperature slash dew point spread divided by 4.4 equals to the base of a cumulus cloud in the thousands of feet above the ground level, AGL. So I hope that kind of makes sense. It was kind of hard for me to wrap my head around it. Honestly, I don't think it's actually necessary to know like what's going on behind there, but I'm trying to break everything down the best I can. Um, but yeah, but this I would follow this for calculating everything. All right, now we get into more clouds that it just wants us to go over for some reason. So we got the cirriform clouds, which are high-level clouds composed of ice crystals, and they occur in fair weather and point in the direction of air movement at their elevation. Pretty cool clouds. We got the nimbus cloud, which form both between 7,000 and 15,000 feet, bringing steady precipitation. Bases of the cloud tend to lower toward the ground when precipitation begins to fall. And then we have the cumuliform clouds, which is a vertical clouds form rising air base of the cloud indicates where condensation and cloud formation begins. Height will depend on the humidity and of rising air. So the more humid the air, the lower the cloud base. And then we got the stratiform clouds. They can cover the entire sky like a blanket. You kind of see those like on dark gray, gloomy days. And cloud bases usually only have a few hundred feet above ground level. Or hills and mountains, they tend to reach ground level like in Minecraft. Like, when you're up at build height and you see those clouds, those would be the stratiform clouds because they're like going right through you. And so those might be called fog. And occasionally, as fog lifts from the ground from daytime heating, they can form into a little stratiform cloud. So yeah, here our we got our cirriform clouds, our nimbus clouds, our cumuliform clouds, and our stratiform clouds right here. I low key be forgetting the names, but yeah. All right. What is the approximate base of a cumulus cloud if the surface air temperature is at 1,000 feet MSL, if is 70 feet Fahrenheit and the dew point is 48 feet Fahrenheit or 48 Fahrenheit? Pay attention to the MSL part. It's gonna try and trick you. Um, so we got 4,000 feet MSL, 5,000 feet MSL, or 6,000 feet MSL. And the answer is 6,000 feet MSL. See, we go through everything. We do the dew point minus the temperature, and then that divided by 4.4, which is, so we got the spread here, and then it's 4.4. And then multiply that to 5,000 feet above ground level. But since we're messing with the MSL, we plus it by 1,000, so it's 6,000 feet MSL. And MSL is just the mean sea level. I don't really know. I don't really know what MSL is. I'm not gonna lie. But it's different, apparently, so look out for that. Um, Alright, now we got stable air characteristics. So, if you're in stable air, there will be stratiform clouds, smooth air, obviously, fair to poor visibility in haze and smoke because there's no wind blowing all that smoke away, continuous precipitation because there's no wind blowing those fronts away, and it's cold and dry. Things about this is moist, stable air moving up a mountain slope produces stratus type clouds as it cools. I don't know why it says status. I'm so sorry, guys. It's so late. It's 1 a.m. Anyways, steady precipitation preceding a front usually indicates a warm front. This results in stable air with stratiform clouds and little turbulence. Unstable air characteristics. We got cumuliform clouds, turbulent air, good visibility because there's wind, showery precipitation, and it's warm and humid. So when air is warm from below, it rises and causes instability, which is like, yeah. As lapse rate, and we talk about that in 7.4, increases, air is more unstable. Turbulence in clouds with extensive vertical development result when air rises. Well, unstable air rises. Sorry, Space is hiding some keywords here, bro. All right. 7.10 question. Clouds with extensive vertical development over mountainous terrain are signs of dry abiotic lapse rate, a stable air mass, or an unstable air mass. So this was kind of a trick question. It was an unstable air mass. If it was a stable air mass, the clouds that would be developing wouldn't have a vertical development. They would be straight stratiform clouds. All right, final section. All right, temperature inversion. When temperature increases with altitude instead of the normal where it decreases with altitude. This usually results in a stable layer of air. Develops near the ground on clear, cold nights with light winds. And this is called by terrestrial radiation, which sounds crazy. I don't know why they use that word. It's like, what is that? It's just that it's just heat from not head, I don't know why it says head. Okay, it's the heat from the ground that shoots up into space. That's what it is. The heat I think it means like terrain radiates space. Yeah. Um with temperature and radiation variations, can cause minimum temperature to occur just after sunrise. And you're like, what's minimum temperature? And that's just when the atmosphere is losing more heat than it's gaining because the heat from the ground is stronger than the heat from the sun. So basically, even when the sun is up a little bit, it's not warming up because the heat from the ground is still stronger. Um, Smooth air with restricted visibility is usually found beneath a low level temperature inversion. I think it's restricted because fog might be forming. I'm not sure. Alright, final question. Temperature and radiation variations over land with clear sky typically lead to minimum temperature occurring after sunrise, outgoing terrestrial radiation peaking at noon, temperature reaching a maximum closer to noon than to sunset. And the answer is A. It's not any of that noon stuff, it is the minimum temperature. Anyways, I hope this video was somewhat helpful to anybody who's reading the Gleim, but it was definitely helpful to me for studying. Let me know if I got anything wrong, please. And I hope you have fun flying.